Let's say our goal is to synthesize carbone. And in organic chemistry, one of the things we learn about is the fact that none of our reactions yield 100% product, and we're going to get side products along the way. And one of the problems is that because these pathways are so similar, we get byproducts with very similar chemical characteristics. And this makes our life very challenging if we wanted to create a pure product. And so one of the techniques that chemists will turn to in order to purify our products is fractional distillation. And it's essentially the same thing as simple distillation, but with the addition of a fractionating column. And so what I'm going to do in this video is walk through how a fractional distillation setup will work. And to begin with, we're going to look at two molecules, limonene and carvone. And before I go any farther, I'd like us to take a step back and ask ourselves which of these two molecules should have a higher boiling point. And the most obvious difference we see between limonene and carvone, is the presence of this carbonyl right here. Now, what this carbonyl group is going to cause is a charge distribution within the molecule, because the carbon-oxygen bond is going to have a high difference in electronegativity, especially relative to a carbon-hydrogen bond, and because of that there's uneven charge distribution, and this will be a much more polar molecule. So the consequence of having this additional carbonyl, this ketone present, will be an elevation of the boiling point. And what we find if we look up the boiling point of carvone is that its boiling point will be 231 degrees C, whereas the boiling point of limonene is 176 degrees C. So these molecules are almost identical, except the carvone has a ketone, and that ketone is raising this boiling point significantly. And this allows us to perform a fractional distillation, because distillation is a reliance on the difference in boiling point of our components within a mixture. So what we would get in a flask would be a mixture of limonene and carvone, and the first thing we're going to do is heat the flask, and we're going to apply heat. And if you were in an organic chemistry lab, because there's so many volatile solvents around, you wouldn't use a Bunsen burner, you would use a sand bath. We very typically use sand baths in organic chemistry labs because open flames are incredibly dangerous due to flammability reasons. But for the sake of continuing, we're going to be heating this solution. And as we heat the solution, we're going to be heating our mixture, and which of these two components will be the first to evaporate? The component with the lower boiling point, which in this case will be the limonene. And so the limonene is going to be a higher concentration in the vapor phase that is exiting the liquid phase. And so as you're heating it, you have vapor rising, and this first thing that's getting heated, we refer that as the distilling flask, and the vapor phase will enter something called the fractionating column. And the purpose of the fractionating column is to provide an area in which the vapor phase can condense back into the liquid phase. And why is this important? So the vapor that is right here is going to be somewhat concentrated in the more volatile component of our mixture, limonene, but there will still exist some carvone. And going to statistical mechanics, we know that there's going to be a distribution of kinetic energies in these molecules. So just because your vapor phase is going to have some limonene in it, it's also going to have carvone in it. And so what happens within the fractionating column is we're essentially going to condense this vapor, which is somewhat concentrated in limonene, back into a liquid, and that liquid's going to have the same ratio. But as the heat continues to evaporate that concentrated limonene liquid, the new vapor from that will have a slightly higher concentration than the liquid that it just came from. And so that series of evaporations and condensations is going to happen many times within our fractionating column. And so by the time a vapor molecule makes it to the very top of our fractionating column, it's going to be much more concentrated in the more volatile component relative to the concentration just above the surface in our distilling flask. Okay, and so as the vapor phase, now very concentrated in our more volatile component, is traveling through our distillation setup, we're going to pass it through a condenser. And the condenser, as the name should imply, is going to condense our vapor into a liquid. It's going to change the phase. And to do that, we're going to need to take energy out of the system. We're going to do that by running water through our condenser. And so we'd have water entering here, and we'd have water exiting here. And the water is going to take the heat away from the vapor, which is mostly limonene, and the limonene will condense into a collecting flask right here. And so your collecting flask will be concentrated in limonene. It will have a little bit of carbone in it, but certainly more limonene, a higher limonene concentration than did your distilling flask. And what you will find if you plotted the temperature over time of your setup, so the x-axis will be time and the y-axis will be temperature, is that when we get to 176 degrees C and 231 degrees C, we're going to realize some plateaus. And this is an idealized case, but for the sake of understanding the principles behind it, it will help us. And so what we see here is that from, and I'll call this region 1, and we have region 2, during the time period of region 1, your collecting flask is going to be predominantly whichever component had 176 degree boiling point temperature, and that's going to be limonene. So during T1, it's going to be mostly limonene. And then during T2, the second period, we're going to find that it's mostly our less volatile component now, the carbone, because this is the one that took its sweet time evaporating because it needed a lot more thermal energy in order to change phases from the liquid to vapor phase. And in addition to that, one of the things that you'll commonly find in distillation setups is a vacuum. And it's not always necessary, but the vacuum will help precipitate your liquid within the condenser. And if we ask ourselves why, intuitively it should make sense. So if you have very high pressure on a liquid, it will not want to escape the liquid phase and enter the vapor phase because the vapor that's present in that container is pushing down so hard on it. And so by removing the other molecules present in the vapor phase, you're creating an incentive for molecules in the liquid phase to want to enter the vapor phase. Consequently, less energy needs to be supplied, and this helps us with our condenser. And then finally, you do hear a term called superheating. And superheating is this interesting concept that occurs because of surface tension. So we all know, if we've ever done a belly flop on water, that water has a lot of surface tension and it can be painful. But what we see in the case of distillation is that the surface tension of water will restrict and inhibit the formation of bubbles in a distillation flask. And the consequence of this is we can end up superheating our liquid. And this will be a problem because we want to evaporate our liquid because we want to get a vapor phase that we can put through our fractionating column to condense. So to overcome this, what chemists will do in labs is sometimes they will aerate this solution, the distilling flask, by supplying little bubbles to it, and they also use boiling chips, and the purpose of the bubbles and the boiling chips is to supply an area on which the little bubbles can actually form the vapor phase, where that vapor phase can actually be derived and where it can bubble up. And so that is another key thing you'll often do during experiments. And then this diagram, this little red thing up top, would just be a thermometer. And so this fractional distillation is essentially what you need to know to do benchtop distillation in an organic chemistry lab. And people sometimes will call simple distillation just not having this fractionating column here. So if you don't have this fractionating column and you just go directly from your distilling flask into the condenser, it is just called simple distillation. So they are basically the same thing. I hope you guys find this useful. Let me know if you have any questions, and thanks for watching.